So the last test we're going to learn is the root test. The root test is actually related to the ratio test. In fact, historically, the root test comes first and then ratio test after. So it has basically the same kind of structure. You're taking the limit of something about the terms. In this case, though, instead of being an plus 1 over an, it ends up being the nth root of the an term. So you can guess that that's not always an easy limit to do. That's why we use the ratio test much more than the root test. But sometimes if you have something to the n, this can come in super handy and it's much easier to deal with than the ratio test in that particular instance. So that's why we do learn it. And the structure is the same. If that nth root is less than 1, then you have absolute convergence. If the nth root is greater than 1 or goes to infinity, then you've got divergence. And if the nth root is equal to 1, the test is inconclusive. Do remember that it's the absolute value, just in case you have a minus in your thing. The limit of the absolute value of an. But so where is this helpful? It's really most helpful with, for example, something like this to the n. So I got something in there, but it's to the n. So I've got a function to the power of n. That's where this is helpful. Because what am I doing when I take the nth root? I just will kill that n and then I have a simple limit. Okay. So the nth root of an, and again here, I'll put in the absolute values here, but I don't really need to. No, yeah, I need that, guys. That first one, non-negative. So this is going to be, so the nth root is to the power 1 over n. If I do this, 2n squared minus 9 over 4n squared plus 2 to the n to the power of 1 over n. Okay, so what I'm really going to get is 2n squared minus 9 over 4n squared plus 2. Okay, and now this I can take the limit of easily. All right, I'm interested in n going to infinity, so the fact that the first couple, like maybe what, one term? 1, 2 terms are negative isn't going to make a difference. So the absolute value here, I know it's correct, really isn't going to make a big deal because I'm going to have the same thing as I always do, right? When I have a nice rational function like this, these guys are going to go to 0. I end up with 1/2. In this case, 1/2 being less than 1, so this thing converges by the root test. Okay. Notice, and this is an important thing, if I didn't have an n there, then I would actually have a divergent series, right? Because it would just be this. And that would be something where I could use immediately the test for divergence because that would be this limit. The limit goes to 1/2. Okay? So the fact that I have that n there is really what's driving the convergence here. Essentially, this is a geometric series with a ratio that's pretty close to 1/2. Okay? So what we're really doing when we see something like this, it's a fancy geometric series. I've got something like this. After the n to the nth power. So perfect for the root test because I'm just, what is our real ratio? It's really f of n. Okay, so that's an example of something that you would use that for. Okay, let me do another example or two. Minus 4n over n plus 1 all to the 5n. Okay, not too bad. Again, I'm going to look at the nth root, and I'm just going to write it this way this time. So what I have is I got this absolute value minus 4n over n plus 1 to the 5n 1 over n. Okay, so these n's cancel out, but I still have a 5, and the negative gets killed by the absolute value. So I can just do this 4n over n plus 1 to the 5. Okay, so what is this? Okay, so you can see what's going to happen here. When I take the limit, you know, I can even do this. I can write it this way if I want, or I can just work that out, right? n to the 5 plus 5n wherever. But in any case, as n goes to infinity, this one is just 4 to the 5. This guy is going to go to 1, right? Because I've got n over n, so 1 over 1. So this is going to be 4 to the 5, which is certainly greater than 1. So this series diverges. Okay? Now, some of them you can do either way. You can do ratio or root. So I'm going to do one example, which is an important example. We do it both ways. Okay. This is going to be, I'm going to do n factorial over n to the n. Okay. So first, because you've got, like, in this situation, you've got both a ratio, both a factorial, and something to the n. So with the ratio test, first, so an plus 1 over an is n plus 1 factorial over n plus 1 to the n plus 1 times an, which would be n to the n, and this is going to be, wait, I lost myself here. Oh yeah, n factorial. Okay. Alright, so this is kind of, this looks like a little difficult to deal with. So there's a special way of dealing with this. So I wanted to make sure that we went over that. I'm going to clean it up a little bit first. So n plus 1 factorial, we're going to write it like that. And we got this lousy n to the n, which is going to cause us a little bit of pain. Now here, what do I do with this? I can write that as n plus 1 to the n times n plus 1 to the 1, right? So I'm just breaking this up. If it was like a to the b plus c, it's to the b, a to the c. It just looks weird because it's n plus 1. So multiply this guy to n factorial. And the reason that I did that for a couple of reasons. The first reason is because then, look, my n plus 1 goes away, so that's nice. And then the other thing that I have is that my n's go away. So what I end up with is this. Okay. So that's not necessarily particularly nice. It's this. Okay. And I probably should have done it the other way. I probably should have done, oh, it's in your book. The other way is in your book, so that's fine. All right, that's why I did it this way. All right, so I need to take the limit of this. This is not an easy limit to take, right? Because there's an n up there, okay? This is actually related to the following limit. Remember, there's a couple limits we need to know. That goes to e, right? So, but what is this? If I put this over a common denominator, I get that. What we have is the reciprocal of that. Okay? So, in other words, I can be pretty clever with this, knowing that, okay, these two things are very much the same thing, very, very similar, but one is the reciprocal of it over the other. So what I really want to do here is kind of write this as 1 over n plus 1 over n to the n, right? So this is 1 over 1 plus 1 over n to the n. So when I take the limit of this guy, this goes to 1 over e. Now e is 2.7, so 1 over e is less than 1. So this converges. Okay. But we have to remember, or we have to know what this limit is in order to do this problem this way. Okay. So, we've discussed that with them before. You can just use that, you don't have to prove it. We've proved it. You guys should have proved it in Calc 1. Okay. So there we have it. So we know this thing converges. Now let's see, the point of doing this example was to see what happens when we do it with the root test. This, I don't think that's going to go well at all. I don't think it's going to go well at all. The other way went better. Yeah, that's not going to work out with the root test at all. Because you're going to get n, but then you have the nth root of n factorial. And what are you going to do with the nth root of n factorial? To show that limit, it's not going to work out. So forget it, doesn't work in this sense at all. Never mind. Never mind, this was a good one to do with the ratio test. We'll do another one with an n to the n. With the root test. Oh no, that'll work out nicely. That's not what I want. Never mind, that'll work out. That'll loser. Fine. Fine, I need another example. I'm already at 15 minutes. Before I go, we'll just leave with the root test. Before I go, I wanted to remind you also, in addition to this important limit, sometimes this one comes up when you do the root test. Or instead of just n, if it's a constant, if I have limit n goes to infinity of some constant a, we'll call it c, to the 1 over n, this also goes to 1. So something like that, you can go ahead and just use those limits without having to prove